All right, this is the lesson 4. This is going to be the take it further and the self-check. I'm going to do them together because the take it further is pretty short. So in the lesson 4, take it further, it talks about this meteorologist and climatologist, Dr. J. Marshall Shepard, who works at the University of Georgia, and he was looking at do cities affect rainfall? So if you have a large city, is there more rain or less rain around the city? And then he did this study, and it says down here, the results in 2010 showed that during summer months, there was an increase of rainfall and lightning over the city. And downwind of the city, but not over the surrounding areas. So around the city, right, and so like if you had a city, right, and the wind was moving this way over the city, there would be more rain over the city, right? There would be more rain over the city, and downwind, meaning after the city, there would be maybe a little bit more rain, but all around the city in the other directions, not more rain. And then it talks about some of the explorations here, or some explanations here. And then one of the cities Dr. Shepard said it was Houston, Texas. He found that it rains more in Houston than surrounding areas. What do you think will happen to the rainfall amount if Houston grows larger? So I said that the rainfall amounts would likely increase in the city because, according to his study, he's saying that the city is increasing the rainfall. And one of the cities that was true was with Houston, Texas. So if Houston gets bigger, I am imagining that the rainfall would also increase. And then it says, make a diagram to show how cities might affect rainfall patterns. So what I did was so over here we'd have the cycling. This is only partially completed at the moment. So in the most basic general idea, we have water vapor, right? This would be like water vapor. Water vapor is over here, right? And then we have the wind direction. So let's say that this is we've got farmland over here. So this is a farm. We've got farmland. So we have water vapor that's in the air. Now, as the wind direction carries the water vapor to the city, right? The city is, because of things we've read up here, perhaps the city surfaces are going to warm up that air. So the warmer air is going to rise and condenses. And then that's when it would start to rain, right? The warmer air is rising because the city is heating it up. Whereas over here, evaporation happens faster than condensation. So we have the water vapor is not condensing, right? Because it's colder, so the water vapor is kind of like evaporating and staying up as a vapor in the air. So that's a pretty basic way you could diagram it out. 3. A physical model is a miniature version of some part of the real world. How could you model how a city affects weather? Describe your physical model. What might you use to represent? So I typed this out here, but maybe I'll draw it over here. So what I envisioned was you could get like a big fish tank or something, right? And you get this big fish tank, and wait, did I say that? So yeah, I didn't have a thing in the middle. So you'd have like a big fish tank, right? And over this fish tank, you would have, and it's all closed in, right? So inside the fish tank, you would have, maybe like buildings. Oops, this is the line tool. Whatever. You'd have buildings, right? You'd have, on one end, you'd have something that represents a city. And then on the other end, you'd have like a farm over here. Maybe you'd have like a, more like a houses or something like this. So you'd have a city and you'd have houses. Now you would paint these over here, you'd paint everything black. And over here, you'd paint everything white. Or you could actually just paint it how it would look, but you know, I'm saying paint it black and white. So it would, because the black would have, it would increase the amount of energy that the city is absorbing and make it hotter. And that's kind of what it talks about here, is that the warmer surfaces, the darker surfaces, right? It says dark surfaces such as asphalt absorb more energy. So I'm thinking like just go to the extreme for a little model. Make the all city black, the whole city farmland all painted white, and then you can have lights above it, right? You'd have like those big like kind of uh, you know garage type lights, right? And then be shooting the light down into this open tank. And you would put water in the tank somehow. Maybe you fill it with water. Maybe you have like a tray of water in here, so it can, so the water can, you know, be. So I'm trying to diagram water without, it won't change. Let me change colors. Anyways, so what would happen is with these lights in here, this is, you've created kind of like a greenhouse effect going on, and the water vapor would start evaporating right into the air of the tank. And as that water is evaporating into the air of the tank, you would think that because it's warmer over here, right? Because this is, right, this would be all black over here. Right? These buildings would be dark. So they'd be absorbing more energy. So I would imagine, I don't know if this would work, well, you know, I'm trying to model something here, but that it would cause the vapor to condense more on the along the top of the tank over the city than it would maybe over here, and then you could show like, oh wow, look, it does. That is why it's doing that. Okay, and then there is this historical weather data for the city. In this one, you actually have to go find some historical weather data. So I actually put a link in the weekly document that helps you do that for Sacramento. I did it for Los Angeles. I did a different city, and I noticed that it did actually look like there was a line that increased. Let me see if I can show you this. Where'd it go? Where'd it go? Oh, I didn't put it there yet. Oh no. I'll have to go back to that later. But anyway, there was a chart. You'll see if you follow the link to go to Sacramento's, and you could see that there was a chart, and it went up ever so slightly. And if you looked at the beginning, and it was talking about average rainfall, so you could see over the last 100 years it did actually increase. Okay. Describe how accurate you think her forecast will be. And so you should say something about, I'm not, these are your own words for your statements, but you should be saying something about her forecast should be fairly accurate because it's only for 5 days out, and you know, it looks like she's using real tools over here to actually measure those things. It's almost the same exact kind of answer I gave in the lesson with that thing. And summarize evidence you've gathered to support my claim. So my evidence that I supported is I know that they're modeling things. So the farther out you model, the less accurate it's going to be. I see that she's using weather patterns over here, cold weather, hot weather, maybe pressure systems going on. You know, so those my evidence of how she's getting her forecast. This one right here. Using a ruler, draw a single straight trend line that comes to as close as possible to the points and extend it to 40. So this doesn't start off looking like this, right? It looks like that. So you got to draw a trend line. So my trend line was, I started kind of here and went up through them like that. Your trend line might be a little bit different. There's actually math ways to draw trend lines, but we're just winging it. And then it says, using a ruler, draw a single. Oh, see, now I said 34 first because I think I drew my trend line a little bit more like this the first time, right? And so it was about 34, and this next time I drew it a little bit up more like that, so 38. So I'd say either of those answers would be fine, depending on how you draw your trend line. We're not using a computer to draw the trend line and get averages. So it shouldn't be 42 because 42 it's going up like this, and you can see if it's up to 42, it's kind of hovering above all the dots, and you don't really want that. And if it's at 32, that would be down here, right? 32. And that's like hovering below all the dots. So you'd really want 34, 38, something in there. One of those would work. And all models have limitations. By drawing a straight trend line on this graph, we are assuming the rate of change is constant. It's always like the plant. This is talking about a plant growing. The plant is always growing essentially at the same rate, which we know isn't true with plants because eventually they'd get to a certain size and they'd stop growing almost entirely. And if the rate of growth changes as the plant ages, the line would not be straight. So, eventually if this was, like if you're drawing a trend line of how a person grew, right, they would be getting super tall when they're little, and then it kind of like goes like that because they don't grow at all, and then they get old and they start shrinking. Currently it is snowing in Fargo, right? Here's Fargo, it's blue, moderate to heavy snow. It's likely to rain in Knoxville tomorrow. Knoxville's right here. Knoxville's right here, actually. There's a little arrow and it's right here in this open space. But it's likely to rain tomorrow in Knoxville because a cold front is moving towards the area. This is the cold front. It's blue and the arrows are pointing that way. It's moving towards this way. This is the warm front and it's moving up north. And then I rated these actually based off of the time. So no, I didn't really even look at the map. I did a little bit, but then I realized that probably the more important thing is tomorrow it will be snowing in Fargo, in 4 days, and in 7 days. So these are all spread out enough that whatever the forecast for tomorrow is, that's going to be much more accurate than 4 days out or 7 days out. And 4 days out is still a big difference than 7 days. So I rated these in accuracy based off of how far out into the future they are. And finally, why are mathematical models so valuable to scientists who study complex phenomena like weather? They help us to simplify. You can read this, but they help us to simplify really complicated things, and it allows us to use computers and look for patterns in things and model things that would be just really hard to do without mathematical models, right? If you didn't have a mathematical model to model something, you didn't figure out like, oh, if there's half as much grass, there's going to be half as many rabbits. If you could dwindle it down to something like that, then you'd have to take readings much more often, and it would make predicting things much harder. And weather forecasts are made by analyzing various weather data and determining the probability that certain conditions will exist in the future. Explain how the accuracy of a weather forecast model is tested. So how could you, this question is asking you a different question that we haven't seen before, and it's how could you actually test these forecast models? And so what I said was, well, because let's say all the different news networks are using different forecast models, or maybe different states or different governments are using different type of mathematical models to model things. Actually, in the United States, pretty much every news network actually uses the same exact models based off of NOAA, which is the NOAA, which is the National Organization for Atmospheric, I can't remember what it stands for. But they all use the same thing. So, but how does that organization's models compare with, let's say, another country's? Well, what you could do is you can use their models. What I said down here is you could use those models for a year, right? And you could say like, okay, we've used these for a year and they were really accurate on these days, right? You could find out when the model was really accurate, really close to its predictions, like where was the real weather close to the predicted weather. And then you could look at when the real weather was not close to the predicted weather. And you might look for a different model, right, that performed better. Did someone else's model for measuring rainfall at this time of the year work better than yours? Because if it did, then maybe you can tweak your model a little bit to include what the more accurate model did. So it would be like just anything else in life, over time, you could imagine you're, doing sports and after a year of, practicing sports, you realize, hey man, I'm not really good at doing this one thing. I'm really good at these things, but these other people are better at me at these things. And you kind of look at, well, what are they doing to make them better at these aspects of, the sport? And that's kind of what you're doing with the model. You're saying like, well, where is our model not working? And whose model is working better than ours in that situation? And you can kind of borrow some of those ideas. Maybe they have different equations or different ways that they've programmed the equations to work together, things like that. That's how you could improve your model and test if it's accurate. Testing if it's accurate would just be seeing how close it is to the forecast. That is all for these.